Hey, folks. Right now we're going to talk about conservation of momentum, and then I got one example for you, I believe, on this one, and I'll have some more examples after. But for now, talk about conservation of momentum. So, if you look at Newton's second law, all right, over here, that's the way he wrote it in his book for the principle. And basically, he said net force is the rate of change of momentum. So if you're applying a net force to an object, its momentum will change, aka it will speed up, slow down, or turn. Okay. So we're going to use that idea here along with Newton's third law. This is a good Newton day. So let's say we got two carts. One's moving and it hits the other one. A hits B. Okay. And let's ignore for now friction between the carts and the ground and all that, although it doesn't matter, but let's ignore it for now. Just keep it simple. So when the collision occurs, will B's momentum change? Okay, well, yes, it will. Okay, here's why. When A hits B, there's going to be a force, the force of A on B. Okay, and that will force B to move to the right. It will change its momentum. It's gain velocity, clearly. Okay. Now, at the same time, though, we know that B hits A to the left. So that's the force of B on A. And A's momentum will also change. It will lose momentum. It was moving to the right, and at the very least, it's going to slow down here. It could even turn around. Its momentum would change sign then. Okay, so that's definitely a change. But here's the deal. We know that the force of B on A and the force of A on B have to be equal. That's Newton's third law. So Newton's third law leads to an interesting consequence. If we look at the AB system, there are no net or unbalanced horizontal forces acting on the two-cart system. A and force of A on B and the force of B on A are equal, and for the system that I've highlighted in yellow there, those two forces cancel. Okay, so that means the net force on the system is zero. That means the momentum change of the system is zero. It doesn't mean there's no momentum. It means there's no momentum change overall. Now, what did happen is B gained momentum and A lost it. But the amounts are exactly the same. So if B gained 20 units of momentum, A lost 20 units of momentum. The total momentum is the same. It's just like if you and me had our wallets out and you reached into your wallet and gave me a $20 bill. You lost 20 bucks, I gained 20 bucks, but the total amount of money in our two wallets didn't change. Okay, it's the same idea here. So conservation of momentum is a result of Newton's third law. Newton's third law is incredibly important. It leads to conservation of momentum. It was the reason for conservation of energy. It's probably his most important law of motion of his three. Now, how we write this is we say the total momentum before the interaction is equal to the total momentum after. Now, one more note on this. Momentum is a vector. I put arrows over both those. So direction matters here. So for instance, if something has a momentum of 20 to the right to start with, a system, then the system has to have a momentum of 20 to the right after. So it could have a 30 and a 10 like so, and that would still be a total momentum of 20 to the right. So the sign direction matters, okay? So let's try this out. So first example, well, actually, I'll come back to that. So here's my first example. Okay, let's say I've got two carts that are like so. We got cart one, cart two, and let's say there's a spring between them, and you have compressed the carts together. The spring is compressed right now, and let's say it's compressed 40 centimeters. So these carts, you're holding them together, and they really want to fly apart. And this left-hand cart, we'll make it 1 kilogram, and we'll call it A. And the right-hand cart, let's make him 3 kilograms, and we'll call that cart B. Okay. And let's say, so you're holding these carts together, and then voila, you let them go. So they're going to fly apart, right? So let's say after they're flying apart, you measure the velocity of cart A, and you get a velocity of A. It's to the left, so we'll call that negative, and that's 6 meters per second. Okay. So we're going to calculate two things. We're going to calculate the final velocity of B after they left each other, and we're also going to calculate the spring constant K, the newtons per meter for the spring constant. Now, a couple notes about this, okay? direction matters. So we're saying to the right is positive. Okay, so that's the first thing. And our system is the two carts. And you can say the spring too, but the spring doesn't move much, so I'm not going to worry about that. All right, so the total momentum before they exploded. Oh, and by the way, this kind of interaction is called an explosion. And all that means is the two objects start together and end apart. So anything where there's at least two objects that start together and end apart is an explosion. All right, so for these explosions, total momentum is going to be conserved. Now, before they exploded, what was the momentum of cart A? Well, it was 0. It wasn't moving. How about the momentum of cart B? Well, that was also 0. Okay. Afterward, we have, well, we'll just call it MAVA plus MBVB. That's the momentum of each cart after they exploded. So on the left side, we got a big fat 0. On the right side, MA is 1, VA is -6, MB is 3, and what's VB? Well, hopefully you can do that in your head. VB is +2 meters per second to the right. Now, many of you probably guessed that well before we did the problem. This is an easy one, but it's still good to go through. So that's the velocity of B at the end. What's the spring constant? Okay, well, here we're going to talk about energy. Before the explosion, the spring had elastic potential energy. After the explosion, the spring gives up all that energy to the two carts, and that becomes the kinetic energy of cart A and the kinetic energy of cart B. Now, a note, these are capital Ks. This is up here is our spring constant, a small k. So I'm sorry they look similar, but they're different. All right, so we got everything here except for the spring constant. This is 1/2 k x squared equals 1/2 ma va squared plus 1/2 m b vb squared. Okay, we can cancel the halves out. There we go. Those are gone, and we have everything in here but k. X was 0.4. That's 40 centimeters squared. Equals MA, which was 1, VA was 6, got to square that, plus MB was 3, and VB was 2, and got to square that. And if you do your math here, this is a 36, and this is a 12. So 48 divided by 0.4 squared. If I do that in my calculator, I get, what do I get? I get 300 newtons per meter. So that is your spring constant. Now, there's one more very important thing that you need to know about explosions in general. Okay. First of all, what happened to momentum? All right. Well, momentum was conserved. It was the same momentum before as there was after. Before there were zero units, and when I add this plus this on the right side, I get a 0 units. Okay. So the total momentum was conserved. Whenever two objects interact, if that's your system, if there's no external forces to that two object system, momentum is going to be conserved. What about kinetic energy? Okay, not just energy. I'm asking specifically about kinetic energy. What was the kinetic energy before these things collided or before they exploded? Well, it was 0. Afterward, it was 1/2 mv squared plus 1/2 mv squared, which should be half of 48. It became 24 joules. So the spring had 24 joules of potential energy to give up, and it gave it to the two carts. So in general, for explosions, kinetic energy is gained. Okay, so we got two ideas here. Momentum is conserved, but kinetic energy is gained. Kinetic energy has to come from somewhere. In this case, it came from the spring. Now, other examples of that, I would say you are throwing a ball. Well, therefore, the energy, the kinetic energy of you and the ball, especially the ball, comes from the food you ate that day. If you have something like literally exploding, like let's say a cannonball leaving a cannon, well, there the energy came from the gunpowder. Okay, so that kinetic energy has to come from some other source. All right, so the next example I'll show you is what's called inelastic, collisions. So we'll talk about that next. I hope that was helpful. Have a good one.